Okay, we're on YouTube now, and I'll give a few moments for people to sign in. Sorry, folks, for starting a little bit late. We had a few technical difficulties, but they've been sorted out. Okay, I think that's good. Thanks everybody for joining us on this, what is it, 5th day of the Chandra Data Science Workshop. Today's session is a very exciting session. Evan, can we get the session slide, please? We have a variety of speakers today, as you can see here in this list. Our first speaker is coming to us from Saclay, and it's Fabio Acero, who's going to talk to us about blind source separation techniques for X-ray spectro-imagers. Fabio, can you please share your slides?
Yes. So let me take the screen now. So can you hear me okay?
Yes.
Okay. So I'll stop my video share for, I have a small bandwidth here. Yeah. So, all right. So yeah, this talk is going to be about how we can use and analyze X-ray data, and in this case, Chandra data here, taking fully into account the fact that the data are multidimensional in nature, and in X-rays, so this is slide 2 here, we have an incredible luck in X-rays that we have been using integral feed units, the one we call IFU, for a long time now in X-rays, and since the 70s, 80s, and in particular with the CCD revolution in the 90s with CCD cameras with ASCA. And in fact, for each photon, we can measure the position of the photon, the energy, and the time of arrival. And this is what we've been doing for 4 decades now. And this is an example here of if you look at the point source here, in this case, it's a pulsar, and there's going to be a small animation in here where you see each photon coming into, arriving into the camera. And yeah, the animation doesn't work here, but let's move on. And so we can really measure here in the data cube space as a function of Ra, Dec, and energy, and we can see and measure individually those photons. And this is something that has arrived recently only in optical, for example, with Muse, and that has brought a great revolution in the analysis of those large cubes. So what kind of science can we do with spectro-imagers? So there are many different use cases. For example, you can isolate point sources and try to study the diffuse emission, or you can isolate some features in extended sources. And here below are examples of the Perseus galaxy cluster and of the SN1006 supernova remnant. And in these cases, for example, you can map physical parameters on those extended sources, for example, the temperature of the plasma, or for example, in the case of the supernova remnants, you can have a map of the abundances of certain elements. But the issue in order to do that is that, of course, those extended sources, all the physical components are entangled, they are mixed together, and it's not easy to separate them. And on top of that, you have projection effects because those objects are 3D objects, and you have a projection effect. And so how do you disentangle the projection effect and the mixing of the different physical components? And usually the way we do that is that we define, here is an example where you define small individual boxes. And in those boxes, you can do that adaptively, for example, with the adaptive Voronoi tiling, where you do a size of the bin that is proportional to the number of count. And you want small bins when you have a large number of count, and larger bins when you have low statistics. But the problem is that those cells are defined on the surface brightness and not directly on the number or the complexity of the mixing of the different components. And then you end up with, typically in this case, you have more than 10,000 individual spectra that are extracted, and it makes the spectral analysis a bit painful. And so the issue here is that we really have at the beginning a 3D data cube, and then we are going to treat independently each cell from their neighbor. And so you do 2D, a map, and then 1D spectral analysis. And so you're not really fully exploiting the data cube. And so it's a bit like we are looking at the X-ray data that are, if you have time, it's even 4-dimensional data. And we always look at one side as the image, and we do a morphological analysis, and we go to DS9 and we look at the images, and then we define some region of interest based on that, and then we project it on the other side and we only look at the spectrum. But we don't have for now really tried to really use the full 3D information. And so if you look at the Casey data set with Chandra, it's a very deep exposure, megasecond exposure. And here I'm going to show a movie that shows X, Y, and the Z dimension is the energy. And so this is really what the data set looks like. And so you can see in the depths here, those are the emission lines. And we can recognize some enhancement. So the color coding is yellow and red means that you have a higher density of photons. And if you look in the energy dimension, you can recognize that the density is enhanced in some regions. And this is the emission line, but that we view in 3D. And so you can recognize some strong silicon emission lines, for example. And even you see the islands of iron emission. And just from the data cube, you can see that the position in energy of the iron line is not exactly the same in the north and in the south. And this is the redshift that is known, but you can really see it here directly from this movie. So how do we generally analyze data in high energy? So mostly here I'm going to review X-rays and gamma rays. So the way we do it generally in X-rays is that, let's take an example of a composite supernova remnant where we have a shell and a p-win in the center. So if you want to extract the spectrum for the p-win, you draw by eye an ellipse around the p-win. And in the on region, in this circle here, you both have the on and also the off. So you also have some contamination from the diffuse emission from the remnant. And this is what we do in X-rays and also at TeV energy. Another possibility is, this is what is done usually with Fermi analysis at GeV, is that you do a morphological, parametric morphological analysis in which you say my source is a disk, which has a thermal spectrum, plus an ellipse that has a power law spectrum, for example. And but the issue is that it works okay for Fermi, where you have a low spatial resolution, a low, not very good PSF. But here, of course, the assumption that my supernova remnant is a perfect disk is not good in X-rays. So what kind of morphological assumption do you use? Reality is not only made of disks and Gaussian, especially with sub-arc second PSF. So the other thing that is possible and that I'm going to discuss here is to do a blind source separation method in which you use the full 3D information to disentangle the supernova remnant from the p-win because they don't have the same morphological and spectral signature. The p-win has a synchrotron emission, and the supernova remnant here is dominated by thermal emission. So let's explore a bit those two kind of analysis, the 3D parametric one and the non-parametric blind source one. So one thing that we have been investigating in the last years is to apply a method that is called the generalized morphological component analysis that was initially developed to extract the CMB map from the Planck data. The main idea is the following one, is that the CMB and the electron, the synchrotron map from the galaxies, they don't have the same spatial distribution, and they don't have the same spectral distribution. They don't have the same spectra. And so you can use and leverage that diversity, morphological diversity, to separate them. So the assumption here is that you can represent your data cube. So in Planck, you also have a data cube with a linear combination of a spectrum convolved with an image plus a second component and so on and so forth. And in this case, when we say blind source, we mean that we want to estimate all the spectral component and the image component with no prior information. And in this case, for example, in those kind of methods, you will fix the number of components that you want to retrieve by hand. So a bit of detail of the algorithm is that, so you're trying to minimize, you're trying to estimate A and S. They are the spectra in the image. Both of them are unknown. And if you don't know, so you have X equals A times S in matrix form, and you don't know A and S. So this is an ill-posed inverse problem. And if you want to solve that, you need to add a constraint to that problem. And here, the idea is that they have different morphology. And this is implemented by saying that they are sparse in the wavelet domain. And so this is the general idea. And you will estimate A and S with alternate estimation of them. So in one case, in the step one, you will estimate S, the images for a fixed spectrum A, and then you do the other way around and you try to minimize this with the data fidelity term. So you want that the solution looks like your input, and then there is this sparsity constraint term that I mentioned. So an example will speak more easily than the equation. So this is an application to the CASE Chandra dataset. Just in 2004 dataset, there is about 200 million photons in 1 megasecond exposure. So this is really a gold mine to try those kind of methods because you have lots of statistics. And so the input of the method is this data cube around the iron line between 5 and 7 keV. And without any other sort of information, you say to the method, I want 3 or let's say 4 components out of that are morphologically diverse and spectrally diverse. So they don't look the same in the images, and they have different spectral signature. And the output are the 4 images that you see here. Black is a total spectrum, and blue is the individual spectrum associated to the image. And so this is the result of the linear decomposition. And so you see a component that has filaments and a powerless spectrum that we associate after with a synchrotron component. And then some line features that are associated with known redshifted and blue shifted iron structures. So in another paper with a PhD student, we investigated deeper around each emission line, and we were able to find the images of the redshifted and blue shifted component for all the intermediate and heavy elements. And so this is something that was not possible before. We knew that there was some redshifted and blue shifted component, but we didn't have the mapping of those elements and those redshifted and blue shifted component at the arc-second resolution. So this is really a 3D view of the asymmetry of those heavy elements that is possible by that method. And scientifically, what we derived is that most of the emission that we see in X-rays is redshifted. So there is an asymmetry. Most of the emission is going away from us. And this is similar to what was seen with a new star for the titanium-44. And if you see the plot on the right, you can see that most of the emission is red, and the red is going at the opposite direction from the neutron star. And this is something that is compatible with the numerical simulation of core collapse explosion. So this is for the blind source. And then I wanted to mention a word about the 3D analysis that we do, for example, with Fermi or with CTA. And I tried this with gamma pi. So I'm also involved in the CTA Cherenkov telescope collaboration. And so the idea of a 3D analysis is that you want to represent your data cube as a model, for example, here a point source, and then you convolve with the exposure curve, with the background. You also convolve with the redistribution matrix, the RMF, the PSF, etc. And you move the parameters in order to reproduce the full counts cube. So it's like in expect, but you have the extra spatial dimension. And so why is that useful? So the idea is that with the 3D analysis, so first, the Chandra data are 3D or 4D. And so you will benefit for doing an analysis directly in the 3D space, and you fully take into account the entire information in your data. And so you don't have to define directly a region and ellipse by eye and an on and off region. You model everything at the same time. So it's more complicated, but in the end, the sensitivity is higher for the faint sources in particular. And in this 3D space also, if you subtract, for example, a bright point source that you have in the middle, this allows you to study the underlying faint diffuse emission in a better way. So I tried quickly with the Chandra data, and currently Qiao and Sherpa do not provide 3D products. So I did a mix of Sherpa to use the XPEC models and reading the files, and of GammaPy that is designed to do that 3D fitting. And currently it works. I was able to do a simple analysis with some basic assumption. And there are identified some of the hard tasks that are still to do in order to do a realistic, really full 3D analysis is, for example, generating an exposure cube with vignetting as a function of energy, a cube. So it's not only 3 energy. I have really to construct a cube with hundreds of slices in the cube, a PSF cube and a background cube, for example. So this is a question for if there are some members of Qiao and Sherpa in the team. I would be happy to discuss whether there is some interest to explore that more in detail. So
2 minutes.
Okay, so I have 2 slides left, so that's perfect. And in the near future, of course, we have Athena and Lynx that are on the horizon, and they will bring a transformational view of the spectral X-ray universe. And this is an example of a simulation I made for the Tychoid supernova remnant with XIFU, in which you really see a lot more detail in the spectral cube here. And those data cubes they will have a tremendous number of voxel if you look in the data cube. And so we need really to consider new methods to fully exploit the wealth of information that will be available with Athena and with Lynx to really make the best out of those incredible data sets. So in conclusion, so there is really a huge amount of photons in the archival dataset already in Chandra. And so to really fully exploit those datasets, I think we could try to explore those 3D methods that I mentioned. And this method, there are other blind source separation method, can be applied to all extended sources, supernova remnant, P-winds, clusters of galaxies, the diffusion emission in the galaxy, or even time cubes, for example. They can also work with all spectro-imagers, and there are a lot of spectro-imagers that are coming online. And we have developed also a different version of that tool, especially one tailed for the X-rays, in which we do the Poisson, we handle the Poisson statistics. And also something that we're working on is to try to constrain a little bit the spectral. So the spectral part, we don't want any kind of spectrum. We want something that belongs to the power law family. So you can learn the metric of power laws as observed with Chandra, and you can try to project the spectra and add one constraint on this by learning the metric. And so you need a large number of photons. It doesn't work if you have a 10 kilosecond exposure of a faint source. And yeah, as I mentioned, it will be interesting to see whether we can do a 3D-like analysis in the Chandra dataset. And yeah, as a conclusion, so there is a lot of archival and future higher spectral resolution spectra coming along, and there will be Chandra archive are gold mines already, but you still need to dig even if you're sitting on a gold mine. So we need to explore, I think, and this is what has been shown this week and last week also, try to explore those new tools that you really can leverage on this gold mine that are those X-ray archives. Thank you.
Thank you very much, Fabio, for that excellent presentation. Very interesting work and results. If you have any questions for Fabio, please add them to the Q&A here or into the Slack channel if you're watching us online through the YouTube stream. We have a question from Aneta. Thank you for an interesting talk and saying, yes, it would be good to add 3D capabilities to Sherpa, and any contribution to the Sherpa development via GitHub is welcome. So if you're interested, Fabio, in working there, reach out to Aneta for.
Yeah, Aneta, thanks for the comment. Definitely get in touch via Slack.
Johannes is asking a question. The spatial spectral fitting improvement over on/off is interesting to him. Compared to just spectral fitting, how much more computationally expensive is it?
So this is something that we have been investigating. There were some tests on the CTS, or in the Cherenkov telescope array. That is currently under construction. We made a data challenge and we tested the difference between the significance of the detection of just in 1D and the significant detection in 3D, and you definitely have a boost in significance detection. And the cost, the computational cost, depends on the complexity of the region that you have to model, because in 3D you have to model everything in the data cube. So if you have 10 sources, you have to model all the 10 sources in your field of view and not just one. So it really depends on the complexity, but it's not much more really computationally expensive. Of course, if you want to, in gamma rays, if you want to do a 10 by 10 degree with 100 sources, it's going to be much more expensive. But otherwise, it's not that crazy expensive.
Great. Thank you, Fabio. If you have any further questions for Fabio, put them in the Slack and Fabio will join you there to engage in discussion. I may put a question there myself, Fabio. Our next speaker is, thank you. Our next speaker is Hui Sun. And can you start sharing your slides? Joining us from the NAOC, and is going to talk about a unified binary neutron star merger magnetar model for the Chandra X-ray transients, CDF-S XT1 and XT2. Take it away.
So can you see my screen right now?
Yes, I can.
Okay, thank you. I'll go ahead. And good morning and good evening. I'm Hui Sun from a National Astronomical Observatory of Chinese Academy of Sciences. And I think my title has already been introduced, so I will quickly go through my talk within 5 minutes. So when we talk about the binary neutron star merger remnants, there are a few possibilities. For example, in some cases, it will collapse into a black hole directly, or bear some short stages like hypermassive neutron star or supermassive neutron star, or in some cases, it will lead to a stable neutron star. While if we compare the electromagnetic counterparts for various merger remnants cases, like here summarized for black hole and the Magnetar, which is the supermassive neutron star case, or the neutron star which is fastly spinning. And if we see the EM counterparts from different viewing angles, there are some similarities like the short GRBs and optical emissions in like more isotropic viewing angles. There are also some difference, like it is predicted that the X-ray emissions will be powered by the dissipation of the magnetic wind if the merger leads to a magnetar, and the X-ray emissions will last around several hundreds to 1,000 seconds. And this will be more like isotropic emission, so it will have much wider solid angle compared to the short GRBs. Previously, in the observations of short GRBs, we have seen some light curves in the X-ray afterglows or in the extended emission of the short GRBs. So the light curves show a flat case and the later decay, usually by around T2-2 or even a deeper slope. And these are more can be more interpreted as the X-ray emission powered by the magnetar. While as we have introduced that the X-ray emissions are more isotropic, so we developed the model that with viewing angles dependent light curves. Here summarize the light curves from different viewing angles. So in the jet zone, we expect the X-ray emissions in magenta color as a company of the short GRB, while in other regions where, like in the free zone, there is X-ray emissions can freely escaped, and it shows the X-ray emissions with no short GRB accompanying, while in other regions like the ejector place, the X-ray emissions will get absorbed by the ejector first. So we call the trapped zone. The light curves will just emerge later and show, like in some cases, first emerge and later decay, or in some cases it will stay as a plateau for a shorter period. And by the observations of short GRBs, we don't have much events like the X-ray emissions with short GRB-less events. While thanks to the Chandra Deep Field South Survey, there are two very interesting candidates. The first one we call it CDFS XT2. So the light curve here shows a flat X-ray emission, followed by a decay with the temperature of T2-2. So this is an excellent candidate as expected from what we have in theory from theories.
One minute.
Thank you. And the offset of this source with respect to the host galaxy is also consistent with what we expect from short GRB, like the binary neutron star merger events. Another fast X-ray event is called CDF-S XT1. So you might see this one is published earlier than that one, but the light curve is more different. So the light curve shows a faster rise followed by a general decay. If we compare this light curve to other like the X-ray transients like short breakouts and X-ray afterglows of short GRBs, there are some distinct properties of this one. So later we developed a unified model to interpret it, both the two transients, while in the XT2 is more like in the free zone, where the X-ray transients is from the dipole radiation of the Magnetar, while the XT1 is more like the viewing it is observed from the trapped zone. So the X-ray emission get absorbed at the beginning and later escaped. So we fit both the transients using this model and derive the parameters, which is marked here as the B field and the initial spin period, as well as the constraint on the ejector mass from the XT1 transient. And these parameters, if we compare them with those X-ray afterglow or X-ray plateau observed from short GRBs, they are more like stay consistent with each other, as well as the consistency in the host galaxies with short GRBs. So here shows our my last slide, which is so we expect more transients like the XT1 and XT2. Actually, like in 3 months ago, Chandra also published, showed a detection of a fast X-ray transients in a tail, which is very similar to the event of XT2. And in the future, we might expect the wide field of view telescopes like the Einstein probe. So the Einstein probe has a field of view of 3,600 square degrees in the X-ray soft X-ray band, like 0.05 to 4 keV. So this is very ideal to catch the fast X-ray transients like this XT1 and XT2. Also, we can expect the multi-messengers and multi-wavelength detections to play joint detections of both these multi-wavelength signals. So thank you.
Thank you, Hui-sun. That was a very interesting talk. Lots of exciting things to come. If you have any questions for Hui, please put them into the Slack channel and you can engage with Hui there. As our next speaker to start sharing their next slides, as we are out of time for this talk. Our next speaker is Lia Corrales, coming to us from the University of Michigan, is going to talk to us about PyXsis, a lightweight Python package for loading and viewing X-ray spectra.
Thanks so much. I'm really excited to talk to you about this little package that I put together called Pixies. First, I want to talk about why I created Pixies. The main reason is that I love Python, and in particular, I really love the object-oriented programming workflow, which is very different from an XSpec workflow and the workflow that a lot of other tools, which are kind of inspired by XSpec. So this package does not require a HiaSoft installation. It really just depends on some of the core Python libraries that we use in other wavelengths, such as specutils, which was developed by AstroPy, depends on NumPy, and also depends on matplotlib for plotting. So another reason I developed this package was because I needed unreserved access to the counts histograms in many of my spectra, and in particular background spectra. So I developed this package in order to do my 2020 work on Saclay star. And in that particular case, the different background spectra that I were selecting are shown here. I needed to filter them, I needed to stack them, and I did that all independently. But then when it came to modeling, there weren't really a lot of tools or the basic analysis that we use for background spectra with other software tools really makes a lot of assumptions, which are generally true for Chandra HETG, but really not the case for Saclay star, where the background was very significant and needed a non-physical parametric model. So on the right here, I show some plots that I made using Pixies, as well as the models that I created with Pixies. And then why else? I also just wanted to create my own custom fitting statistics, in particular MCMC, and applying priors to those statistics. And those tools aren't as easily accessible, at least at the time when I started this analysis. And I wanted to create my own models as well. So for instance, I'm working in Python models to create a RIAF, or radiatively inefficient accretion flow model for Saclay star built on PyAtomDB. So of course, this isn't something that is exclusive to Pixies. You could hack together models and use them, I'm sure, with Sherpa or PyXspec. This is just one of the reasons that I develop in Python. So I want to go through the object-oriented workflow that I'm talking about that is supported by Pixies. So in an object-oriented workflow, each X-ray spectrum is loaded as a separate object, which you can think of as a container for all of the information that's associated with that spectrum. So this 1D spectra are built on the specutils framework, but it contains additional information such as your bin edges, your spectral regions that you want to notice, your binning, for instance. And then the ARF and RMF files are actually associated with the spectrum, and they're loaded as separate objects, which are then linked to or contained by the main spectrum.
2 minutes.
Thank you. So with Pixies, you can also set up models as separate objects following the API set by the model superclass. This model takes the edges of the energy bins for your spectrum as input, and then it returns a model flux spectrum, which I've just labeled as mflux. So this is just a NumPy array, which contains the model flux for each bin that's associated with your spectrum. So if you apply this mflux and send it to your spectrum, it will run this evaluate model function, and it will apply the ARF and RMF to yield a model counts histogram, which is also just a simple NumPy array. So I intentionally left out the fitting because this is the place where the user gets to decide, how am I really going to treat this data analysis? So in theory, you should choose your fit statistic. That includes making a choice about what statistics you're using, such as Poisson or Gaussian. You can apply priors and things like that. So you would supply these two arrays, the counts, which are contained in the spectrum, and then the model counts, and calculate how good the model is. And then you need to pick a fit optimizer. So the very many options, you can use MCMC provided by MC or PyMC3. And then there's also plenty of optimizers provided by the SciPy package. And then these two functions that the user creates together will be used to update model parameters and run this process again until you get your best fit. So if you want to combine models, it's actually not really the easiest thing. You would have to create your own model function to put together a bunch of model objects, combine them in the way that you desire, and then spit out an mflux. But again, it's very highly customizable. So just to summarize, I think Pixies is helpful if you want unrestricted access to the spectral data that you're working with and to perform a highly customized analysis. On the positive sides, it's really easy to install. It's easy to load and plot Chandra HETG spectra in particular with the matplotlib framework. So even if you're not using it for analysis, it might be helpful for plotting. You could also potentially consider using it if you want to incorporate information from other multi-wavelength data sets, if you already know how to use those data sets with AstroPy tools or other Python-based approaches. But it is a lot of extra work to combine models. The fitting is intentionally left out, so the users really should be defining their fitting statistics and algorithms to be used. And something like line identification is already provided by a different package, such as PyAtomDB. So it's not great if you're just trying to do a really quick fit. In that case, use Sherpa or PyXspec. But Pixies does provide scaffolding if you plan on developing your own Python-based spectral models, custom fitting algorithms, or just want to take advantage of other publicly available scientific computing packages in Python. And I'm happy to have collaborators fork me on GitHub, play with it. Yeah, thanks very much.
Thank you very much, Lia, for that interesting presentation. I'm sorry I got the name wrong of the package.
It's okay.
That's all the time we have for this talk. So please put your questions for Lia in the Slack if you want to carry on the conversation or have a question for Lia. I'll ask our next speaker to please present their slides. Great. Our next speaker is Asif Iqbal, from Paris-Saclay, and is going to talk to us about non-parametric machine learning technique for deconvolution of temperature profiles in galaxy clusters. And I see your keynote environment there. Yeah. I see. If you see on the upper right, you can click the switch, the little, the two boxes with the cross arrows by the X all the way to the right.
Oh, can you hear me now?
Hi, I can hear you now, but your slides are in presenter mode. So
okay.
if you hover, you'll see there's a switch over on the right. Over on the right side of the screen. You see the two squares with the arrows on the side of them. Further right, where you see the big gray X.
I don't see.
Oh, let me see if I can annotate this one here.
Okay.
Click that. That should switch them. Is it not switching them?
No. Okay.
Okay. What you can do is instead of showing, show them like this. That'll
okay.
work. Take it away.
Okay, let me start. Hi, everybody, and I'm postdoc at CEA Paris-Saclay, and today I'm going to talk about convolution of temperature profiles in galaxy clusters using machine learning technique. Now, first of all, galaxy clusters. Galaxy clusters are the largest, or not only the largest collapse objects in the universe, they are also the endpoints of structure formation. This makes them as important probe of large scale structure of the universe. About 85% of the galaxy cluster mass is composed of dark matter. 10% is in the form of hot baryonic gas called intracluster medium. And this is the compound that is actually observed in X-rays. Remainder of the mass is in the form of stellar mass in galaxy clusters. Now, as shown in figure, galaxy cluster exist in variety of dynamical states. Relaxed clusters have a high degree of spherical symmetry and have high density and low temperature cores, while disturbed clusters have low degree of spherical symmetry with high peaked core emission. It turns out X-ray emission is directly proportional to square of projected gas density. The figure here shows the typical density profiles recovered from the X-rays. The X-ray spectra also allow us to estimate the temperature profiles. However, we look at a large number of photons in a bins. So temperature data is relatively scarce as compared to density profiles as shown in here. Now, the spatial X-ray studies provide us important details about the thermal history of the ICM, the astrophysical processes going on, like the shocks and cavities. They help us to estimate total mass and dark matter profiles in the galaxy clusters, and they are also useful in cluster cosmology. However, one needs to have the precise estimates of temperature profiles as well as their gradients to make them as precise cosmological probes or astrophysical probes. Ongoing project called Checkmate project, which was originally called the Heritage project, is an example of the use of galactic clusters as a probe of structure formation and cosmology. It has a 3 megaseconds of acceleration observation time that was proposed by Monica Arnaud and Stefano Tori. The project is currently led by Gabriel Peth and Stefano Tori. The Checkmate sample is as a selected sample, therefore it's many biased, and it includes a total number of 18 clusters. The clusters are drawn from the Planck SZ2 catalog, which are shown in the solid points. The ultimate aim of the project is to study the ultimate products of the structure formation in mass and time by studying most recently from galaxy clusters called tier 1 clusters, which are shown in the blue points, and the most massive clusters called tier 2 clusters, which are shown in the red points. And the observations are tuned here in such a way that to get precise estimates of temperature profiles and hence entropy, pressure, and total mass in the galaxy clusters up to the R500. The technique that I'm going to discuss today is developed in principle to make most use of such precise data sets. No difficulty in estimating the true temperature profiles in galaxy clusters. No, the 2D observed temperature profiles is obtained by fitting the isothermal model to the spectra in the ring. One such ring is shown here. However, the spectra in such rings is actually the combination of different spectra at different temperature at different radii due to the projection effect along the line of sight and also due to the PSF effect. Moreover, the equivalent temperature is simply the sum of average temperature of the different components. We have a nonlinear temperature dependent scheme modeled by Wittgenstein and Mozart, yielding us the so-called spectra-like temperature profiles. What this means that the convolution matrix W which is used in the fitting is complex and is itself a temperature dependent, and that one cannot use a simple standard non-parametric deprojection techniques to obtain the true temperature profiles. One standard approach is to use the parametric model such as proposed by the Wittgenstein et al. It is a 8 parameter model. 4 of the parameters corresponding to cool components of the relaxed clusters. Our approach is to use our main aim is to have a more generic approach, which is adapted to which is more adapted to the variety of types of clusters that we see in X-rays. Now, before discussing our deconvolution technique, let's talk about the manifolds and manifold learning in a couple of slides. Now, in the top figure, you see the temperature profiles for a subsample of Planck selected as a cluster. The temperature profiles or the T are normalized by Tx, and the radius is normalized by standard quantity R500 here. You can see there is some sort of similarity in the profiles. This is also seen in the corresponding 3D temperature profiles derived using the Wittgenstein model. This is where the manifold hypothesis comes in which we assume that the data does not occupy the whole ambient space, but is actually concentrated in a lower dimensional space. Then the goal is, aim is to find this lower dimensional submanifold by learning the underlying structure, the key features in the data. So, so in principle, we can find the complete, have the full description of the manifold, but that requires an unfeasibly large data set. Our approach, our use specific points of specific temperature profiles that we call the anchor points or anchor profiles basis, like say T1, T2, 3T here in the manifold, such that the interpolation among these can yield us any physically relevant temperature profiles found. Here, the interpolation is performed using the base centers, which I'm not going to discuss here due to the lack of time, but this is described in this paper. Now, our deconvolution technique is inspired by standard autoencoders, the principle of which was nicely explained by Michelle in her talk last week. So I will briefly talk about it. The figure here shows a standard autoencoder. The input layer takes the data, in our case, the temperature profiles. The goal of the encoder, phi, enclosed in red, its job is to map this input data into lower dimensional space. The middle layer here called the coded layer or featured layer in principle should contain all the information about the underlying structure, the key features of the data. The job of the decoder psi, enclosed here by in blue, is to transform this low dimensional representation of the data into true real representation at the output layer. Okay, I had this in animation, but I will try to explain it. This encoder and the decoder is the autoencoder that I explained here. It's in the more abstract form. So the board parameters, the encoder and decoders are learned by minimizing the difference between the training sample and the reconstructed profile, temperature profile, T delta J. So in our case, we use a library of 165 galaxy clusters obtained using XML Newton data and the Wicklehin model, evaluated at fixed fine grid points. Now, this autoencoders requires much more larger data sample, which is not possible in our case. What we rather use is a special class of autoencoders that we call interpolatory autoencoder. It's a combination of standard autoencoder plus what we do is the interpolation in between using the anchor points that I discussed before. So what we do here is that the output of the autoencoder for any profile from the training sample Tj is it which is phi Tj is present in terms of the anchor point profiles phi Tis by optimizing the weights lambda i's in this equation. After learning this decoder knows a function that we call AIEA model. This is essentially basically the correspondence between the weights lambda I and the reconstructed temperature profiles. That's to say that the decoder represents our 3D temperature model, which is the functions of the lambda i's. So this is our main model to get this 3D temperature profiles. Now, since then, we have this 3D temperature model, which is a function of lambda i's, where I is the number of points, anchor points used. We can convolve it with the convolution matrices to get the theoretical 2D projected data points, temperature profiles, which can be then compared with the observations to get the true value of the temperature profiles, that is T3D. We use standard publicly available MCMC package and the Gaussian likelihood in our estimates. So now the question is which anchor points or profiles and how many anchor points we use in our analysis. Currently in our model, the anchor profiles are carefully chosen temperature profiles from the training sample. However, they can be learned during the learned during the training stage of the sample itself. In our analysis currently, we used 4 different anchor point sets. Set A has a minimum of 2 anchor points, the anchor profiles, and set B has 5 anchor profiles. Now this figure here shows the results of our analysis with our AIEA model for a typical RADAX cluster with different basis sets. The green lines in all cases represent the median 2D temperature profiles, along with 1 sigma error bars that we get when fitting the data are represented by the blue points to the AIEA model. The figure at the bottom shows the corresponding posterior distribution of the parameters. As you can see, the parameters are relatively well constrained. In principle, the fit should improve as we increase the number of points, that is from set A, set D. You can see the fit in A is relatively poor as compared to other profiles. The improvement in fit from set B to set C or set C to set D is marginal, and it's not visible with the eye. This figure shows the results of analysis for the disturbed cluster. Here, unlike in the previous case, the fit in the set A is relatively good. However, we see in fit D, we see some extra features. I forgot to mention the sign line represents the 3D temperature, corresponding 3D temperature profiles we get with the best fit. So here we see that the 3D temperature profiles have some extra features. With the set D, it's unclear whether these are the true features or as a result of the all fitting or the statistical outliers.
2 minutes.
Okay, so currently we are looking at it, and we are trying to include the simulations in our learning stage to access this kind of features. Here also the parameters are relatively better constraints. Now conclusion. We introduced a non-parametric framework to construct the temperature profiles, and this technique takes all observational effects into account. That is projection, PSF, and nonlinear effects. We're currently improving the library by including results from the numerical simulations. We're trying to quantify this model with respect to choice of basis we use. We're extending the learning stage by including the estimates of the slopes of derivatives. This is crucial in the mass estimation of the galaxy clusters. And finally, we're trying to extend the analysis to the full checkmate sample. Thanks.
Thank you, Asif. If you have any questions for Asif, please add them to the Slack or put them in the Q&A. We have a few moments for questions. Asif, I will add if you have any have you done any comparisons with this using simulated observation?
Not yet. So that's what we're trying to do now. We're trying to improve the simulation. So in our training sample, we use that we have used the Wickling model. So this may be biased. We don't know. So but to have the more clear picture of it, we're trying to use the simulation results, numerical simulation results in our training sample.
Yeah. And with what, in addition to the Wickling model, what other models are you considering? Simulations.
Simulations. Okay, we have to use simulations which have AGN feedback, which have supernova, everything. So we will have a profile. So it will not be a more. I don't think there will be a parametric model. So yeah, that's all.
Okay. Great. If we have no more questions, I will tell you, if you're thinking about questions, to put them in the Slack channel. In order to keep the session somewhat on time, I'm going to go ahead and move forward now with our next speaker. Our next speaker, if you can start sharing their slides. Thanks again, Asif. Our next speaker is Marc Gagné from Westchester University, and is going to talk to us about synthetic X-ray spectra soup to nuts. Marc, you are currently muted. There you are.
All right, can everyone see me? So I'm gonna have to speak very quickly here. This is a lightning talk. So this is work that I've been doing with my collaborators at the University of Notre Dame and the folks at MIT, specifically with the Orion VLP data. So this is a 2007 image of the trapezium cluster, and the bright source in the middle with the readout streak and the pileup is theta 1 Ori C. This star is unusual in that it is a magnetic massive star. And what we observed back in the 90s and again in the mid-2000s with Chandra is essentially variability caused by the fact that this unusual star with a magnetic field is also rotating. The magnetic pole, the magnetic dipole, is tilted by about 45 degrees with respect to the rotation axis. And then the inclination of that rotation axis to our line of sight is another 45 degrees. And what this means is that this induces variability. At phase 0.0, which corresponds to X-ray maximum, we see the magnetic pole. And then when we see the magnetic equator half a period later, we see the X-ray minimum. And just to give you an idea, this is a slow rotator. And actually the reason it's a slow rotator is because of the magnetic torquing that's been happening for the last few 100,000 years has spun the star down. So rather than being a rapid rotating O star with a typical period of a few days, this has a period of 15.4 days. I'm going to stop this. I'm going to show you another simulation now. This is a two-dimensional simulation showing you how these shocks form. So I'm going to let this loop a little bit. There's a lot of detail here. We start the simulation off with a dipole like the one I just showed, but then eventually what happens very quickly is that the wind actually pulls open the field lines outside the magnetosphere. So what you see in this simulation is actually density or log of density in gray, along with the shock temperature in the colors. And the shock temperatures here are running from about a couple of million degrees all the way up to 200 million degrees. And the key point here is that the X-ray shocks form in the places that are not dense. In fact, these models allow for all kinds of cooling, radiative cooling, inverse Compton cooling. And effectively what happens is that as these shocks form, as they cool, they become denser. And so the key point here is that the X-rays that we see, the X-ray luminosity, are coming from the regions at the interface of the cool dense plasma and the hot, very hot shock plasma. So now what we've been doing for the last couple of years is doing 3D simulations. These are simulations with Pluto, and the upper panel shows you where the X-ray luminosity is coming from in a 2D slice. And the panel below is showing you what the 3D luminosity looks like looking down on the X-ray disk, and the blue lines represent the magnetic field in the simulations. This is now the Orion Very Large Program, the Chandra data that's been obtained now over many years of Theta 1 Orion and the other sources in the trapezium. And this is a combined 2.1 megasecond spectrum. And what I'm showing you here is what we're going to be trying to model over the next year. Each one of these observations are typically about 100 kiloseconds. So we have about 25 or so of these individual observations, and we will be able to do phase result spectroscopy. So why did I want to talk about this in the Chandra data science workshop? So this is more of the spectrum showing you all the line identifications. And as you can see, the Chandra spectrum, the data are beautiful. We see the continuum, we see the line profiles. We even see that the line profiles are not strictly Gaussian, that there is these Voigt wings that we can actually explain from the simulations. So why is this in a Chandra data science workshop? It has to do with what to do with these three-dimensional simulations and how to compare them directly with Chandra data. So to give you an idea of how we do this, this is a view looking down on the disk. This is X-ray maximum. And this is a slice through the 3D data, but to actually do the line profiles, we consider the entire three-dimensional volume. And essentially we do a convolution. We do an emission measure weighted velocity profile. And from that, we generate a line profile. So this is the first time that this has been done. And so what we have here is a predicted line profile for this star based on this model. And what we find is a Doppler velocity of about 4 to 450 kilometers per second in this particular snapshot. Now, if we want to know what the X-ray line profile is going to look like at X-ray minimum, then we take the data that we have here, which is the emission measure. This is again a slice in 2D, but we use the 3D data. And what you can see here below is what the velocity looks like at this time from this viewing angle. And the key point here is that even though this is a slow rotator, you can see that there's actually a rotational profile. So that even though the velocities near the surface of the star are relatively low, they actually get quite large as you go out far away from the star. And that's what actually contributes to some of the broadening that we see. And the prediction now is that at X-ray minimum, we should see narrower lines actually than we see at X-ray maximum. So that's one of the things that we want to test in the data. And the last thing I want to talk about is that we've been using the Pluto code, which is a widely used MHD code to do some of these 3D simulations. But the Pluto code uses conventional spherical polar coordinates. What we have developed over the last year and a half, this has been primarily with the team at Notre Dame, is a new way of doing three-dimensional simulations using using a geodesic mesh. And essentially, this is based on an icosahedron with 20 faces, which is then made into a sphere, a spherical icosahedron, and then is subdivided many, many times in order to give us the angular resolution that we want in our 3D simulations. And then we extrude that over the entire volume of the wind, the magnetic wind outside of the star. This is a simulation from one of these simulations. And I simply want to advertise a paper that is coming out in the next couple of months in monthly notices, which is the first paper, first astrophysical paper using this geomesh code. And then our next steps are going to be to add the full energy equation, therefore allowing us to actually model the shock physics. So the next year should prove to be very exciting. And our hope is that this kind of modeling will be essentially the prototype for modeling many, many massive star systems. All right, that's it.
Thank you very much, Marc. I have questions that I'm going to put in the Slack, and I encourage other people to put your questions for Marc in the Slack as well. That's all the time we have for this talk. We're going to move now to our invited speaker. Will Francesca Chadha-Day please start sharing your slides? Our next speaker is Francesca Chadha-Day from Durham University, and is going to talk to us about giving us the invited talk on machine learning for Axion searches.
Having slides as virtual background.
Today seems to be the day for
the sharing, I'm afraid.
Yeah, today seems to be that day for some reason.
It will only let me share my slides as a virtual background, which I think might look a bit odd.
Yeah. Interesting.
Okay.
So there should be a basic tab on the top of your share.
Yeah, so it's just maybe it won't change unless I go into and out of it. Yeah, so it says it's clicked on basic, but then the options that I have are just slides as virtual background, computer audio, video or content from second camera, which seems, yeah, that's also what's under advanced. It's just not
You don't see the application with the slides and listed there
no,
anywhere.
it's just a PDF, so it shouldn't be you know, shouldn't be terribly complicated. I think maybe I could email them to you. Would that work? If your screen sharing's working?
If you can, yes, and do that, and then maybe talk a little bit about what you're going to speak about while we're preparing that.
Okay. Sorry about this, everyone.
Send them to me first, but yeah. If you have them on a Dropbox or something, just put the link in the chat. This is the first time that I've had this many problems in one session. So I wonder if I need to update Zoom or if we all need to update Zoom. We might be having a clash with versions.
Okay, so I've emailed you the slides.
Okay.
And I'll just start talking to kind of make the most of the time. Hello everyone, I'm Fran. I think this talk is going to be slightly different from other talks in this workshop because I'm primarily a particle physicist rather than an astrophysicist. And the reason I'm talking at the Chandra Data Science workshop is because there are potentially lots of particle physics discoveries to be made with Chandra data. So today, right, they're here now. I'm going to be talking in particular about searches for a hypothetical new particle, the Axion with Chandra, and in particular improvements we can make using machine learning. This is primarily based on this paper that you can hopefully see on the screen now that I wrote with collaborators in Munich. And in particular, I'd like to give due credit to Simon Schallmoser, who did really the bulk of the coding for this work as part of his master's thesis and who has just started a PhD. Next slide, please. Oh, great. Okay. So to start off with, I'm just going to talk a bit about what axions are and why we should care about them. Then I'm going to talk about how we can search for axions using galaxy cluster physics and how we can use machine learning to help with and improve this search, of course, with a particular focus on Chandra observations for this process. And then we're going to give the results of our initial work and conclude. Next slide. Sorry, if I'd known someone else was going to be changing the slides, I wouldn't have used so many slides. So I wanted to start off with just a little bit of an overview of why we're doing this. You know, why have I just picked this particle, the Axion, and said, well, I want to go and search for that. And we're at a position in particle physics at the moment where we know there's dark matter, you know, matter out there that we see its gravitational effects, but we don't see it in any other way. And we don't know what it is. And a lot of theoretical physicists have spent time trying to think up what dark matter might be. And, you know, this plot shows just some of the possibilities for that. So you can see we're really suffering from too many models and not really any data kind of supporting or refuting any of them. So we're at a point where we need to think of ways to really go and find out more information about what dark matter could be. And in particular, in many of these models, dark matter does have a very weak coupling to standard model particles such as the photon, meaning that we might be able to find it by looking at astrophysical data very carefully. Next slide, please. So my work has primarily been on one particular particle, the Axion. This image here is because the Axion was named after a brand of washing up liquid, which is sort of joke because it's meant to clean up the problems of the standard model. So why do we care about axions? What do they do? What's good about them? So axions are ultralight new particles, hypothetical new particles. They're predicted in a lot of string theory models. They explain null measurements of the neutron electric dipole moment, i.e. the strong CP problem. And they can also act as both dark matter and dark energy, depending on their mass. Now, the work that I'm doing doesn't actually rely on axions being the dark matter. It just relies on axions existing there in the model as a degree of freedom. But obviously, if one were to find evidence for an axion, it would be a very promising dark matter candidate. Next slide, please. So how do we go about searching for axions? Well, one of the most promising ways is using the fact that axions have a very weak interaction with photons. So that's summarized by the Feynman diagram on the left, showing an interaction vertex between the axion and two photons. And in astrophysical environments, this mainly comes into play when one of these photons is kind of replaced by a background magnetic field. And in particular, in a background magnetic field, axions and photons can interconvert. The process is kind of similar to neutrino oscillations or even to Faraday rotation, where photons of different polarization rotate into each other. The axion effectively acts as a third photon polarization. Now, the strength of the axion-photon interaction is parameterized by this parameter G. It must be very small, otherwise we'd have seen the axion already. But if axions exist within some range, we don't know what this value of G is. And of course, the higher G is, the stronger any axion-photon effects. Next slide, please. So there's already been a huge experimental and observational effort to find axions. So this plot shows some of the axion searches. On the bottom here, we have the axion mass. So you can see that it's very light and also can really exist at a huge range of masses. And on the y-axis, we have the axion coupling to photons. Now, the yellow line here is about expectations for the QCD axion, the axion that solves the strong CP problem in particular. But more generically, axions can exist across this plot. All of the other kind of colored regions on the plot are places that have been excluded by particular experimental searches, where experiments have been performed which demonstrate that there is no axion with that combination of parameters. And of course, there has been to date no real experimental evidence for axions. There have been some claims of kind of hints, but really nothing conclusive. So, for example, the green lines labeled haloscope are the result of axion dark matter searches. So they rely on if axions are the dark matter, that dark matter on Earth converting to photons. And the blue region is an exclusion based on null searches for axions produced by the sun. Next slide, please. This slide is very mathsy and the details aren't very important. But the main point is really just to show how Axion photon interconversion works. So you can see we have this kind of vector on, you can't see my pointer, but the thing that's a column vector, thanks, with the X and Y photon polarizations and the axion. And the propagation of this column vector is described by the mixing matrix to its left. And you can see that this mixing matrix has off-diagonal terms. I'm assuming that Faraday note rotation is negligible at the moment, but otherwise there would also be, those 2 zeros would also be filled in. So the off-diagonal terms, these delta gamma ray X, delta gamma ray Y, we've got the formula for in the last bullet point, and we can see that they depend on the background magnetic field, and they also depend on the axion photon interaction. So you really need that background magnetic field there. And this is why astrophysics is such a good place to search for axions, because we have in galaxy clusters magnetic fields over, very, very large distances. And this is where we might see photons turning into axions or vice versa. Next slide, please. So the main kind of strategy I'm going to use to search for axions is to look at point sources that are shining through galaxy clusters. The circle source is NGC 1275 at the center of the Perseus galaxy cluster. That's a very, very bright X-ray source, and it's shining through the magnetic field of the Perseus galaxy cluster, which is kind of, microgauss level field that extends over a megaparsec. And this is going to be the ideal place to search for axion photon conversion. Next slide, please. So the basic strategy is that with an X-ray telescope like Chandra, we can look at the spectrum of something like NGC 1275 or other AGN embedded within or behind galaxy clusters. And if axions exist, some of the photons from these point sources will actually convert into axions in the magnetic field of the galaxy cluster. Now, Chandra can't see axions, so it will look like they've just disappeared. And this is a process we may be able to see. So what we end up with is a kind of photon survival probability from the AGN that without axions would just be 1. But with axions would be different to 1. Next slide, please. So it looks something like this. So this is kind of normalized such that 1 is the astrophysics only result. Of course, some of the photons also disappear via absorption on the way, but that's taken into account in our astrophysics only modeling. Next slide, please. So this is just a zoom in of that photon survival probability on the previous slide. Now, the precise form of the photon survival probability depends on the precise configuration of the magnetic field that the photon travels through. And that's something that we don't know. We have estimates of the strength and coherence length of the magnetic field in galaxy clusters, but I can't tell you its exact form. So that is essentially a nuisance parameter for any axion searches, and that actually severely limits the kind of search potential for axions, in particular if we're hoping to place bounds on axions. However, whatever the magnetic field is, there are some kind of generic features of the photon survival probability when axions exist. The first one is that it's less than 1, because some of the photons have turned into axions. This isn't very useful because it tells us that the AGN is going to look dimmer than if there were no axions, but we don't really know how bright the AGN should be. An effect that dims the AGN by 10%, we don't know whether that's axions or whether that's just how bright it was to start with. So that's not very helpful. But the other thing you can see is that we have these kind of oscillations in the photon survival probability. And this is something we might be able to see in the AGN spectrum, and that wouldn't be easily explained just by other astrophysical mechanisms. So that's what we're going to look for. Next slide, please. So as an example, on the left here, you can see the spectrum of the Seyfert galaxy in A1795. And we fit it to a kind of standard model, no axions, just astrophysics, and plotted the residuals. And you can see that the model without axions is a perfectly good fit to the data. And on the right, what we've done is simulated what the spectrum would look like with axions there. So this was just done using Sherpa. And if we then try to fit that with an astrophysics only model, then we see that there are much more significant residuals. And we see this kind of oscillation pattern in the residuals that's a signature of axions. Now note that we don't see the residuals being kind of all very low. We don't see that drop in amplitude because of course the overall amplitude of the spectrum is just a free parameter in the fit. But the oscillations we might be able to detect. Next slide, please. So this technique actually is currently responsible for the leading bounds on low mass axions. So the leading bounds come from work by Chris Reynolds and collaborators. That was using NGC 1275 at the center of Perseus and using the high energy grating observations with Chandra. And these bands are very, very good. You can see that they're quite significantly better than other attempts to search for the axion photon coupling. And of course, I mean, again, I can emphasize that Chris and collaborators found no evidence for axions. Otherwise, this would be much bigger news. But this shows that this technique really has a lot of promise. Next slide, please. So maybe you could just, this was a bullet point list. I was going to go down one by one, but we can just do all of them. That'll be easier. Yeah, thanks. So we might want to see if we can actually improve these techniques. One thing that will lead to improvements is just future X-ray telescopes. So Athena is going to be able to conduct very sensitive searches for axion effects. Another suggestion has been to use Fourier analysis. So we saw that the conversion of photons into axions, the photon survival probability, had this kind of oscillatory pattern. And it's actually approximately sinusoidal in 1 over the energy. So by looking at the spectrum in Fourier space, we may be able to kind of search for that specific imprint of axions, rather than the plot I showed you previously was just done using kind of, is astrophysics only a good fit to the data, yes or no, rather than trying to take advantage of these effects that are particular to axions. Another possibility is to take advantage of polarizing X-ray telescopes that are going to be launching soon, such as IXPE. And this is useful because axions are also polarization active. They would change the polarization of the source. So that's quite exciting and it's going to give us a lot more data to play with. But what I'm going to talk about in this talk is trying to use machine learning to recognize axion spectra. We know that machine learning is very good, for example, at recognizing different kinds of images. So it can recognize faces, for example. It can say, is this picture of a face or not of a face? It does that by, learning what are the key features of a face. So in the same way, we would hope that a machine learning algorithm might be able to learn what are the key features of kind of axion-y data, as opposed to data that, say, just has large Poisson fluctuations. Next slide, please. So as a kind of basic introduction to machine learning and what we're looking for, our ideal scenario would be if I had some very complicated function that could take a spectrum of an AGN in a cluster, DI, that's our input data. And it would output 0 if there is no evidence for axions in this spectrum, and 1 if there is evidence for axions in this spectrum. That's what we want. And what machine learning does is a highly complex fitting process to give us its best approximation to this function. And it does that based on a training set of examples of data that is simulated with and without axions. And again, for the data simulation, we just use the Sherpa fake PHA tool. Next slide, please. So more concretely, what are we doing? So in this work, we've looked primarily at binary classification, where it's just axions or no axions. However, we know that the effect of axions depends on the coupling to photons G, this GA gamma gamma. So what we're actually training is a set of classifiers trained with different values of that axion photon coupling G. And for the training, we use the residuals once the data is fitted with an astrophysics only model. And this is to avoid the complication of the classifiers just learning that dimmer spectra have axions in, because that's not something that we're allowed to use because we don't actually know how bright the spectrum was originally. So we train only on the residuals of the data when fitted with astrophysics only. So for example, we can predict that if I train a classifier to attempt to detect axions where the coupling to photons is very, very low, so it wouldn't be observable, then the classifier is not going to be better than random. But as I increase the coupling to photons, we would expect the classifier to be able to distinguish between data with and without axions in it. And we then want to use these classifiers to place bounds on G, the axion photon coupling, to say, well, axions might exist, but if they do, the coupling has to be lower than some particular value. Particle physicists tend to phrase things as placing bounds, which sounds terribly pessimistic, but is partly because the kind of evidence required for a discovery would be very, very high. I think people are rightly skeptical about any claimed discoveries. And also, particularly when we're looking at astrophysics only, you would really want to confirm discoveries with kind of Earth-based experiments. However, the range of bounds that we can place can also be thought of as the range that we would be sensitive to in the event that we did see something that suggested axions existed. And then just to remind you, because it's a really key point, this coupling GA gamma gamma controls the strength of the axion photon interaction. Increasing G increases the probability that a photon will turn into an axion. Next slide, please. So now we've got these classifiers, we can look at how they perform. So this is an example from the SAFER NA1795, and this is the quadratic determinant analysis classifier. So this isn't even a neural net, it's just using a quadratic surface to try and separate axion and non-axion data. So here on the x-axis, we have the value of G that the classifier was trained on. We then feed test data to all of those classifiers, some with axion, some without. On the y-axis is the kind of mean prediction of the classifier. So every time the classifier returns an axion, it's a 1. Here ALP stands for axion-like particle. And every time it says, no, this is just like straightforward astrophysics, no new particles, it returns a 0. So what are the features of these performance curves? Well, firstly, we can see that for classifiers trained on very low couplings, it's just like completely random. It never knows whether any data contains axions or not. And that's because in this case, all of the test data you fed it in both categories looks the same because the coupling was too low. So the axions didn't have any noticeable effect. So it's not surprising that the classifiers do a terrible job in that case. Now, if we look at classifiers that are trained on higher axion couplings, couplings that are kind of, we think should be observable, we see that if you then feed them data sets that are simulated with axions, these are these colors, then they do very well. They say, you know, yes, there's like definitely axions in this data. Whereas if you feed them data sets that were simulated either with no axions, that's this thick red line, or with just very weakly coupled axions, then they say no axions because the axion effects are much lower than kind of what they've been trained on.
2 minutes.
Sorry, 2 minutes. And for intermediate cases, you get
sorry, 3 minutes.
Okay.
3 minutes.
Cool. Next slide, please. Okay, so the classifiers seem to be working, but we would like to use them to place bounds on axions using what happens when we feed our real data to the classifier. And to do that, we're going to use approximate Bayesian computation. So this is a method that we can use when either the likelihood simply cannot be calculated, or as in our case, it would just be computationally prohibitive to calculate it. So instead, what we do is we try to simulate the posterior distribution. And there's a nice review paper of approximate Bayesian computation here. Next slide, please. So to start off with, we need a summary statistic or test statistic for each of our data sets. You can do this using the full data set, but it's just, you know, the dimensionality of the space really just makes it computationally impossible. So in our case, we're going to use for our summary statistic the highest value of G such that the classifier trained on that G classifies our data as axions. So for data that has a strong axion effect in, we would expect this to be higher. Whereas for data that has kind of no axions in it, we would expect classifiers trained to kind of expect high values of G axions to say, no, there's no axions here. So once we've got that, the algorithm is quite straightforward. We feed all of our test sets into all of our classifiers. Our test sets are evenly spaced in different values of the axion photon coupling. So this corresponds to assuming a uniform prior. In each case, we calculate the test statistic. Now, if the summary statistic of the test data is the same as the one for the real data, when we feed that to all our classifiers, then we accept that coupling. We accept the coupling that the test data was simulated with. This algorithm, of course, only works for discrete summary statistics, but you can do an extension of it if your summary statistic is continuous. Next slide, please. So as an output, we now have a set of axion photon couplings, G, that are sampled from the posterior distribution. And these can be used as an approximation of the posterior. So we can then simply say that values of G larger than the 95th percentile of this approximated posterior can be excluded at the 95% confidence level. Next slide, please. So this is an example of one of our simulated posteriors. So you can see that it's decreasing as we get to higher and higher values of G, which is kind of typical for the data not showing any effects of axions. It's saying that the higher you take the axion photon coupling, really the lower the chance of that coupling existing in the posterior. So we can then just put in the 95th percentile line and exclude values of G above this point. Next slide, please. So the bounds we obtain using this method are given here. G less than about 0.9 times 10 to the minus 12 inverse GeV. And this is a kind of small improvement on previous bounds using the same observations. So it works a little bit better than conventional statistical methods, just using kind of chi-squared statistics, but not hugely better. So we have also started playing with using multi-class classification. So instead of just using binary classifiers for different values of G, training a neural net to say, well, what is the value of G here? Is it 0 corresponding to no axions, or is it a different value? And if so, you know, what is it? And this seems to lead to even greater improvements in the bounds. Next slide, please. Okay, so just looking towards the future, I think there's a lot of work to do here. The work we've done so far has kind of been a preliminary exploration. In particular, most of the results we have so far, the ones for binary classification, are just using kind of non-neural net machine learning algorithms, like relatively simple algorithms. So we'd like to know how much better can we do using a neural net. We'd like to think about combining different sources within the same search, and whether machine learning can help distinguish new physics effects from systematic errors such as unmodeled lines or pileup. And in particular, I think this is going to be important for future X-ray observations. You know, we're going to be getting more and more data, and data of better and better quality. And we would like to know how to really make the best use of that data in searching for axions and indeed in searching for other new fundamental physics. Next slide, please. So this is just to conclude, machine learning has the potential to improve X-ray searches for axions. We may see even greater improvements with future data sets, such as that provided by Athena. And I think that we need to do further work to identify the best machine learning strategies. It's really a huge space of things that one can implement, and it's important to think about which are going to work best. Thank you very much.
Thank you very much, Francesca. Sorry about the early interruption. I meant to add a minute because I said, oh, it takes you 3 seconds to say next slide, please. And I forgot last minute to do it. Great. If you have any questions, please put them in the Q&A here or put them in the Slack channel. We have time maybe for one question. I do have a question for you that I'd like to ask. I know you showed us the simulated spectra that you did in Sherpa. Those are mostly for Chandra observations, is that right? So have you made any attempt to try to predict for those future missions, or is that's for the next steps?
We have, so there's a paper we did in, I think, 2017, looking at axion searches with Athena. That is only thinking about conventional statistical methods. So just looking at the kind of chi-squared of the fit to the data. We haven't done anything with Athena and machine learning yet.
Okay.
But even with conventional statistical methods, you get just a huge improvement, the better energy resolution and the effective area.
Right. One more question I want to ask you. I was thinking of, when I was listening to your talk, I was thinking about how oftentimes when we do a astrophysical fit model and we see something in the residuals, many of us will often think like, oh, I need to add a spectral line there or something. Yeah. Do you think there's any possible observations that might be out there that have seen something, but you haven't had a chance to consider all of them?
I mean, I suppose it's possible. As you know, as I'm sure you know, you very often end up with observations that don't quite fit the astrophysics only model. I think that at the moment, we are really in the position of just setting bounds, because there's kind of so much astrophysics that can go into making things look not quite like they sort of theoretically should.
Right.
However, I think this is going to get better, because I think Athena will show us a much better energy resolution spectrum. So we'll be able to see, if actions did exist, we'll be able to see this kind of classic oscillation pattern of quicker oscillations, lower energies, and then larger spaced oscillations at higher energies. So that would really be something that would start to really look like axions. With the Chandra energy resolution, that's a lot harder.
Right.
And axions also have really distinctive polarization signatures. So if we saw that as well, that would start to look a bit more convincing.
Very nice. Okay, thanks a lot. We have a question about the details for the model.
Oh, yes. So there's the paper at the start. It's just an archive at the moment. That talks in really a lot more detail about the different machine learning strategies, some of which I just haven't had time to cover, and also has references to kind of more to other papers about axions and the original axion work.
Great. I'll put a link to it in the talk discussion channel of the Slack. Great. Thanks, everybody. Thanks, all the speakers. I'm sorry for all the technical difficulties that we had. I am going to end this session and update my Zoom. And well, I may not have enough time to do that for between the next session, but thanks, everybody. I'm going to close this session and restart it for those joining the next session practice. Thank you.